All right, hi everybody. So as I said before, starting next week, we're gonna have in-person classes. So of course, if you're willing to come and you're comfortable to come, please do, and we're happy to have you in the class. Otherwise, we're gonna just continue recording all these lectures, and you can just watch it whenever you want. We'll try to post it as soon as the class ends, so probably an hour or so after. I usually will post it, so it's almost the same as now. We're probably not gonna live stream it through Zoom, and the reason for that is I won't be able to answer questions on Zoom while I'm teaching it in the class. Still, we can do it if you want, but there's really no difference between live streaming it and recording it, because in any case, you cannot ask questions. So your best platform for asking question would be Campus Wire, and that's what I always wanted you guys to be more active on. So if you have questions, put it on Campus Wire. That generates some discussions, and we can even go further than that. So it's usually more helpful even than in class questions. But yeah, so starting next week, I'll see you guys there, or we just record it and you can watch it. All right. Any questions about the logistics before we start? All right. So Tianyu, please go ahead.
Okay, sure.
Hello, everyone. My name is Wenshan Wu. I'm presenting with my teammate Hin Xiang about the paper Honest but Curious Nest. Sensitive attributes of private inputs can be secretly coded into the classifier's outputs. In this paper, the authors raise up a problem that there is a difficulty in distinguishing standard and honest but curious HPC classifier. So what is a standard classifier? So standard classifier is like adult students. They only learn and know what teachers want they know. For example, they only know 1 + 1 is equal to 2. And the honest but curious classifier is like smart students. They not only know what teacher want they know, but also want to explore more knowledge. So they not only understand 1 + 1 equals to 2, they also wonder, how about 2 + 2? In the real world, when the input data is inputted to the honest but curious classifier, the honest but curious classifier will sense 2 attributes. One is a targeted attribute, and one is a sensitive attribute. For example, the input data is a bunch of face. The target attributes for the classifier is their age. However, the honest but curious classifier not only knows their age, but also wonder what their race is. So the race become the sensitive attributes. This honest but curious property is related to something called the overlearning. The overlearning is a model trained for a seemingly simple objective implicitly learns to recognize attributes and concepts that are not part of the learning object and sensitive for a private space perspective. So the overlearning has 2 distinctive consequences. First, the model's interference time representation of an input review the input sensitive attributes. For example, a facial recognition model's representation of an image reviews if 2 specific individuals appear together in it. Overlearning thus breaks interference time privacy protects based on the model partitioning. Second, it can be developed that there is a transfer learning-based technique to repropose a model trained for benign task into a model for different privacy violating tasks. This shows the inadequacy of privacy regulation that rely on express enumeration of learning attributes. So if you're interested in the overlearning concepts, there is a paper here. Next, I want to talk about how much information can a photo provide. So when a photo is provided as an input for the classifier, maybe one of the target attributes is your hairstyle. However, not only the hairstyle can be sensed by the classifier, your race, your age, your facial feature may also be encoded into the output and decoded by those users. Moving one step forward, for example, we have the Apple facial ID. Those facial ID can be logged into your bank account, unlock your phone, and there is so much information in people's cell phone nowadays. Maybe the target attributes is your identity to recognize if these people is you or not. However, there's a sensitive attributes like your bank account, phone number, address will all be encoded into the output and sensed by the honest but curious classifier. So certainly, when there is a picture, it contains a bunch of people, the classifier wants to recognize which people and specific people. The targeted attributes is the recognition. However, the sensitive attributes may be on the location of the people, or the people around the targeted people. Maybe they are your friends, family member. So when the photo is when your photos are used for classifier more and more all around the world, maybe one day a photo can provide all of your privacy information. That will cause a huge security problem. So in this paper, based on this on the problem, there is a difficulty distinguish standard and honest but curious classifier. The author proposed their contributions. I think they didn't share any solutions, but their contribution is emphasize the difficulties of this problem. So for there will be unavoidable privacy attack because we cannot distinguish between those two classifiers. Their characteristics are so similar to each other, and it's very difficult to classify which one is the honest but curious classifier and which one is a standard classifier. And there will also be probability of flaw when an input is inputted to the honest but curious classifier. The output might not only contain the targeted attributes, but also contains the sensitive attributes. Secondly, the honest but curious classifier can encode unsensitive attributes of their private inputs to the classifier's output. In the paper, the author talks about the entropy. Usually, when the honest but curious classifier encodes sensitive attributes of users' private input, the entropy of this classifier will be higher than normal. However, the truth is, the honest but curious classifier can trade some of their curiosity to avoid some defense and pretend they are the standard classifiers. Thirdly, an honest but curious classifier teacher can transfer its curiosity capability into the student classifiers. The teacher classifier is trained on a large labeled data. So the teacher classifier is an honest but curious classifier. When a student classifier has access only to a small unlabeled data and trained on this, there will be knowledge distillation between the teacher classifier and the student classifier. And the knowledge distillation will force the student classifier to mimic the behavior of the teacher classifier. So the teacher classifier is able to transfer the curiosity to the student classifier. So there is a probability that the curious and the honest classifier will transfer their curiosity to all of other student classifiers, all of other standard classifiers. And finally, the author showed their contribution on two real-world data sets. One of them is the UTK-based data set, and another is the level A data sets. There were two data sets contains a bunch of facial informations, and when the authors use some kind of attack and train those classifiers, they found that an HB's honest but curious classifier can be as honest as the standard classifier, while also achieving a considerable curiosity. So that's again emphasize it is very difficult to distinguish between the omnis vacuous classifier and the standard classifier. Next, I will have my teammate Shan to talk about it.
So then I will talk about the evaluation methodology. The author present results in several texts from 2 real-world data sets and discuss the honesty, curiosity trade-off for different attributes. The Celebrate A dataset and UTK phase dataset. The Celebrate A dataset is a dataset including more than 200,000 celebrity faces images. And UTK phase dataset is a dataset including about 23,000 face images in different gender, race, and ages. The top graph is ROC curve of standard classifier, and the bottom one is HBC classifier trained by regularized attack in soft HBC, and target attribute in gender, and sensitive attribute is race. Then the author set the gender as target attribute Y and race as the sensitive attribute S. The training set including 52% male and 48% female, where 42 of the samples are labeled as white and 58 as non-white. The table shows the characteristic of 4 attributes compared to smiling attribute in the training data set. The honesty and curiosity of the table B standard classifier when releasing either raw or soft output, as well as a proposed HBC classifier trained for table C regularized attack and table D parameterized attack. Here, Y equal to S equal to 2. An HBC classifier as honest as a standard classifier will also achieving considerable curiosity. When having access to a raw output, the attack is highly successful in all tasks, and in many cases, people can achieve similar accuracy to a situation where they can train F for specific sensitive attribute. And then the effective of pruning. The pruning figure shows the honesty, curiosity trade-off for different amount of pruning. And the author used L1 norm technology. We can see that firstly, compare the top plot with the bottom plot. We can find the classifier without compression show more tolerance to a large amount of pruning than classifier with compression. But pruning less than 50% of parameter, there is no significant drop in the honesty in both standard and HBC classifier. And lastly, if we prove more than 50% of the parameter, the drop in accuracy for both target and sensitive attribute are significant. For the result, first, we observed that the distinguished HBC model from standard one is not trivial, and typically users mostly do not have technical and computational power and resources to examine the ML surveys before using them. Secondly, for proactive investigations, we need data sets labeled with multiple attributes, which is not always possible. Thirdly, users' data must include several types of sensitive attribute, and even if we aim to distinguish HBC and we may not know which attribute is the HBC model is trained for. As my teammate mentioned, the author claimed that it's very dangerous, but haven't given an effective solution, since it's a very subjective problem and we cannot define the trade-off very objectively. In terms of the future work, firstly, the author believes that the regular technology can help the distinguished standard and HBC classifier are needed, which is the same direction of research in understanding and interrupting DNN behaviors. Secondly, in a limitation of the proposed attacks is that the sensitive attribute has to be known as train time. So people need extending the proposed method or distinguish new method. Thirdly, to investigate the implication of the effective employing a HBC in collaborative learning and multiple ML applications. And lastly, people should know whether HBC classifier reveals more information about each training data set or less compared to the standard classifier. And that's it for our group. Thank you.
All right, thank you. Any questions?
Hello, everyone. Welcome to our.
All right, it's autoplay. I'm assuming it's autoplay of YouTube.
Yeah,
That's what
YouTube.
happens. That's all right. So any questions here? Okay. So it's like this, let me take over. Wait. Okay. So we want to continue the discussion on just introduction and cryptography because we're going to use it later on in the course. And then hopefully on Wednesday, we can start talking about trusted execution environment, which is the main topic this week. So quick recap on things. So I already mentioned about the in-person lectures. Two other things that I want to mention is your quiz. So your quiz would be sometime next week. I'll still not sure exactly the dates, but it will be take home 24 hours. You have 2, 3, 4 hours probably to take it. So you have the full day, and then anytime in the day you want, you can take it. What I will do is that give you some sample problems sometime this week so you can have some idea of what the quiz will be about, but it will be mainly about things that we discuss in the lectures. It wouldn't be part of your readings, but mainly lectures, and it would be open book, open source, everything. So you can you don't have to like memorize anything. And then for your projects, we're gonna have like an open office hour this Friday morning. So starting 10 a.m. I think until noon, I will be available over Zoom. So if anybody wants to chat, the link will be open. Just pop in, talk, and we probably I can have like a running document of just sign up sheets in case that somebody wants to sign up, but try to attend sometime and then talk about your project if you already haven't done so. If you know what's going on and what you're doing, then you don't have to meet with me. All right. So any questions about any of the logistics? Okay, so last time we said that we are looking for a secure cryptography algorithm, right? So we said that we have symmetric and asymmetric methods, and for now we just mainly focus on symmetric, which essentially both the encryption and decryption using the same key, same secret, right? So we are trying to see what is the best way of implementing this algorithm. And we said that ideally what we want to have is this thing called perfect secrecy, where essentially for any two messages that we have in our message domain, there should be an equal amount of chance of the message to be encrypted to some ciphertext C. So there should be exactly equal amount of chance for any message in that message domain. And we said that essentially the problem with perfect secrecy is that, yeah, of course we can achieve it using one-time pad, which it's nothing but just XORing the message with the key. But the problem with that is that it has to be the same size as the message itself. So if you want to encrypt 1 GB of data, you have to have a key of size 1 GB, which is a terrible idea to have. So there are lots of practical issues with that. So we said that, okay, what should we do? And the idea here is that we kind of need to relax perfect secrecy. And that's where we come up with the idea of semantic security. It's not an idea, mainly definition. And the definition is basically relaxing that idea that we have before. And instead of saying that these two has to be exactly equal, it just says that they have to be close to each other with some epsilon, right? And we said that the negligible part, or the epsilon, it really depends on the system and really the assumptions that we have. But typically we are talking about order of either 32 or 64 or 128. So these days we are more tailored to our 128. That's the numbers, 2 to the power of 128. That's usually the number that we are looking for. So 1 over 2 to the power of 128 is what we usually consider as negligible. All right, but it really depends. So there's not like, a standard value or something. It really depends on the system, depending on the class of, activities and so on. And then we're gonna talk about now that, okay, how does the semantic security really gonna help one-time pad? Because remember in one-time pad we said that, you know, M XOR with K will give us ciphertext. So what we're gonna show is that semantic security gonna relax this assumption that K should be the same size as M. But actually, in fact, it's going to be K size would be much, much more smaller than M, and still we're going to satisfy semantic security. All right, so that's where we're going to get to. Before that, let's start understanding semantic security a little bit better. Last slide that I showed last week was this attack game, which essentially is a game between a challenger and attacker. And what we are looking for in this attack game is that at the end of the day, the prediction made by the attacker should be close to random or should be very, very small. All right. So sorry about that. Let me just. Okay. So that's what we are looking for. And then we're going to reduce all of these security mechanisms to some sort of game. All right. So for example, for semantic security, the game would be something like this, where the adversary chooses any two messages that he or she wants, send it to the challenger. Challenger, depending on some random value B, is going to either choose M1 or M2, M0. They're going to encrypt that, send it back to the attacker. Then the attacker can have all the time in the world to actually look at this. And of course, we are talking about exponential, polynomial times, right? So, and then make a decision based off whatever technique he or she wants to use. And then finally make a prediction saying that whether B was 0 or whether B was 1. Remember that depending on the B, we decided to encrypt M0 or M1. And if this is just 50% accuracy with plus and minus some epsilon, we are saying that, you know, this system has semantic security. All right. So we want to have this as equal as possible to a random guess. All right. Any questions so far? So this is just a recap of what we discussed so far. All right, so the semantic security, something that semantic security also implies is this thing called message recovery attack. So what the message recovery attack is basically saying is that if a message M prime, which is a part of the domain M, is encrypted, we are basically saying that the chance that M prime is any part of M is equal to M should be almost equal to 1 over the entire size of message. So what we are saying is that by seeing M prime, any random message, the chance of finding this message should be around 1 over M, and M is just the size of the message space. So let's say we have 1,000 different possible messages. Our encryption mechanism should be designed such that if we encrypt something, the chances that it's actually one of those M's, for figuring out which, if it's one of those M's, is 1 over M, which is 1 over 1,000, right? And then if this M is big enough, then we are reaching to that point that we are saying that it's big enough. So for example, as I said, if, for example, our M's are 128 bits, then the chances would be 1 over 2 to the power of 128, and we are reaching to that epsilon level, right? So we're basically saying that, first of all, our encryption mechanism should be generalizable, uniform enough, and then on the other hand, the message size should be big enough so that the attacker cannot just easily guess, right? So that's one thing that's, semantic security kind of guarantees this. We're not going to show the proof for it, but you just have to take my word for it. And then another thing that, semantic security will give us, it's the chance of recovering individual bits. So that's also quite interesting. So basically, it can be proven that the semantic security guarantees that even single bit of message cannot be recovered by the attacker with probably better than 50%. Right? So it's not like, let's say our message is length of L, right? So it has 0, 1, 2, all the way to L minus 1, right? So it has all these bits. What we are saying is that by semantic security, not only you cannot guess the entire message, but you cannot even guess individual bits with better than 50%. And if you think about it, it's actually, if we can guess individual bits by more than 50%, we can just concatenate them together and get the whole message better than 50%. So there are proof for that as well. So that's why even single bits of the message should not be able to be detected with high accuracy. All right. So that's also another property that semantic security will give us. Again, we're not going to give you the proof for it, but if you're interested, you can definitely take a look at it. All right. So questions so far? Are we assuming that the attacker knows the domain M? Yes. So for example, just say that the attacker knows that all your messages are 64 bits. So basically your domain M would be any number between 0 to 2 to the power of 63 minus 1, right? Okay. So let's continue. So one thing that we kind of like, somebody brought it up last time as well, is the notion of one-time pad versus many-time in encryption. So far what we have discussed is that the one-time pad that we're describing here should be only used once. Why? The answer is simple, right? So let's say we have yes and no, right? And then let's say we have many other things, but let's just look at what yes and no. And let's say for yes, I use one-time pad and I get C, right? I get C1. And for no, I do one-time pad and then do C2, right? So this is one-time pad, everything looks good. And then based off all these things that I already mentioned, the chances of recovering these two is pretty low, so on and so forth, right? But now let's look at the, repeating this example one more time. If I do the same thing one more time, I'll get exactly C1 and C2 again, right? And this is a problem with one-time pad because repeating encryption gives the same results. And that's not good. Why? Because essentially just imagine that for some reason, adversary at first knows that which of these answers were correct. So for example, after a while, they figure it out and so on and so forth. Just by knowing that C1 is actually yes, the next time that C1 happens, they can quickly recover and understand that it was a yes, right? That's one thing. Another thing is that even if that the adversary does not have such a knowledge, just think about like things like zeros, for example, right? So if we want to encrypt zeros and ones, and let's say that the adversary knows that, the frequency of zeros is much more higher than ones. So what we get is some sort of like, a permutation of these zeros and ones. And then just by counting how many of them are zero, so like how many of them are C zeros and how many of them are C ones, they can quickly map this to actual values, right? So this is typically called dictionary search or dictionary attack. So this is usually happens for actual like English language and so on. So let's say, for example, I have a sense word that I want to encrypt. And then let's say that encryption of this will result in some, gibberish kind of, characters, A, B, C, something like that. What happens is that if there is like a one-to-one mapping of this to this, an attacker can quickly just go through a long list of things that we have encrypted and say, okay, for example, the chances that I see A is X%, the chances that seeing B is Y%, and so on and so forth for all the words. They can quickly just do this analysis on the ciphertext as well, and then say that, okay, for example, this C3 is the one that I see a lot. So it means that C3 is mapped to A and C2 is mapped to B and so on. So you kind of like can find a one-to-one mapping between the ciphertext domain and message domain and can quickly basically break our encryption mechanism, right? So this is not what we want to have. We want to have something that is basically randomized and probabilistic, and we're going to talk about it. But just for now, just know that, one-time pad is secure only if you just do it one time. If you repeat it, it's no longer secure. All right. Any questions so far? Okay, so as a result, we need to come up with the encryption mechanism that are randomized in some sense, which means that if I encrypt A multiple times, the ciphertext that I get are two different ciphertexts, and these two should not be equal, or at least a good chance that they're not equal, right? So in that case, it doesn't matter how long the adversary sees a specific, stream or text or string, because essentially every time you do encryption, you just do it with this different criteria, right? So we're going to actually show you how we're going to do it, but it might be a little bit counterintuitive, but we're going to actually show you that how this can be achieved, right? So as I said, so far we are looking for many time, because as I said, one time obviously is not enough. So we are looking for a many time, and we're looking for something that is semantically secure. All right, so that's what the criteria that we are looking at right now is these two things that we want to achieve. One-time pad can give us this, but cannot give us this, unfortunately. So let's see what we can do better. All right. And so I already talked about class projects, so I'm going to skip this. So the idea here is this notion that is called stream ciphers. So the idea of this stream cipher is interesting. So basically, the idea here is that we can start with some small seed, let's say small random value. And then there will be an algorithm, which is the stream cipher algorithm. Let's kind of expand or stretch this seed and make it a long value. And then what we can do is then we can create our one-time pad with this. All right. So so as we're going to show is that if it's not just any seed and any random algorithm, but if we choose these two wisely, then we can show that we can actually have a much more smaller key size. So this would be our original key. We're going to use an algorithm to actually expand this and have a much more bigger key. And then we're going to have our message. And then we're going to use one-time pad here. And then we're going to get our encryption. And what important things this will give us? This will give us the fact that, we no longer need to save a really, really large key. What we can do is just save a very small key, let's say 128 bits or 256 bits and so on. And then use this algorithm here to actually stretch and expand this key to whatever size that we want. So if we want to, encrypt 1 GB of data, we expand it to 1 GB and then do the encryption. Another thing that's going to happen is that, remember I said that the algorithm has to be randomized. So what's going to happen is that we're going to add some randomness as input here. And then what's going to happen is that this randomness change each time we want to encrypt. And this will change the key here. And then obviously once the key is changing, the ciphertext that is generated is also changing. And this way we can have the randomness that be the probabilistic approach that we want to achieve as well. So basically all we need to do is making sure that this random number is changing from one encryption cycle to another encryption cycle. And if you have these two things, then we have our perfect encryption system that is many time and is also semantically secure. All right, so it has both of them at the same time. Any questions here? So the question is the message or the seed being stretched? The seed is being stretched. All right. So so we have a secret information, which is our original secret key, which is like a very small size, 256, 512, something like that. And then we're going to use this in order to stretch it. And then once we stretch it, then we can apply it to any message that we want. So the messages could be any size. And then once we do that, we create our ciphertext, all right? And then we're going to add randomness to this as well. So basically, whenever we want to do an encryption, and we change the random value so that we create a different key and then do that. is the seed. So seed and keys are the same thing. So this the core seed is what we call the secret key. We're gonna stretch it and then let's call it something else, stretch key or key prime, and then that's gonna be used for one-time path. All right. So somebody asked, won't these random seeds repeat after finite period? Yes, but if this is large enough, again, if for example, the seed itself is 128, we have 2 to the power of 128 different possibilities. And this number is very, very large. So it's not gonna repeat itself in years, in hundreds of years. So that's where this notion of epsilon is kind of coming. So we are not saying that the chance that it repeats itself is 0, but is epsilon, and epsilon is, if we use a large number, it would be good enough, right? So do we need to use a certainty? That we're going to talk about this. All right. Any other questions? All right, so to give you a little bit more formal definition, so stream cipher is looks like this. So basically, we're going to have an S, which is a vector of zeros and ones, vector of zeros and ones of size L. So it's number of bits. Then we're going to have our message and our encryption, which is again zeros and ones of size L. And of course, the whole point is that the S is much more smaller than the M and C. So L is actually much more smaller than the capital L. And then our encryption and decryption mechanism would be basically this. The encryption mechanism, the inputs to encryption mechanism would be S and M. And what happens is that the S goes into this G function, which is basically the stretcher function that we're going to talk about. And then we're going to just use one-time path to XOR it with M. And this way we're going to get our C. And then our decryption would be basically the opposite of that. Again, the decryption also has the same key. So the key is going to be stretched again using the same algorithm. And then this time we're going to XOR it with C and get M. All right. So this would be our encryption and decryption algorithm. And the security of this is basically coming from this very, very fundamental thing that for the attacker, it should be hard to distinguish G of S, the stretching function, from a random string, right? So, so basically the whole point of this is that GS should be very similar to any random number that we are drawing from a random distribution. Right? So if the attacker sits somewhere and sees this GS, a sequence of GS for some long time, should not be able with more than 50% just tell it different from a true random distribution. Right? So in other words, the attacker should not be able to guess the next the next GS after seeing lots of GS, right? So we are basically saying that this should be hard. And again, if the proof is actually showing that if the domain for GS is large enough and then GS is actually following a specific pattern, then we can create this, all right? So this GS is usually called pseudo-random number generator, pseudo-random generator. So this is an algorithm that creates random looking numbers, but it's not exactly random, obviously, right? So that's the whole point of these stream ciphers, right? Any questions here? So,
I have a question on that. So, what if we can create a perfect random number generator? Would that create any advantage for the encryption? Or
so we usually cannot create a perfect random number generator. We can create close to perfect random number generators. There are methods for like creating so it's more of like, the quality of the random generator, number generator is still the one that it's important. So there are ways, so I mean, the term indistinguishable is actually has a mathematical formal definition, which is basically saying that GS and a random, what does it mean to be indistinguishable, all right? And then basically, depending on which G you're using, which algorithm you're using, then the distance between this and the actual distribution might be slightly different and so on, right? And that's what we really care. And again, because of the semantic security, all we care is that these two should be as close as together by some number epsilon, right? So we don't need this to be equally to 0. It actually has to be almost epsilon, and that's all we need. And otherwise, we cannot achieve perfect secrecy, because perfect secrecy is for achieving perfect secrecy, we need the entire key to be exactly same size as M. Actually, there is a mathematical proof that shows that if the size of the key is less than the message, you cannot achieve perfect secrecy regardless of what that key is, all right? So that's the whole idea. And one key thing that we're gonna actually talk a little bit about is that the efficiency of the algorithm also matters, because this is, at the end of the day, piece of software in your computer. And then let's say for every transaction that you want to make, for every message that you want to send and all those things, you need encryption and decryption, right? So these algorithms not only has to be secure, but they also have to be really, really fast. Right, so any random number generator that you have, it has to be very quick as well. Not only it has to be kind of indistinguishable from random, but it has to be very quick for querying as well. Does it make sense?
Yes, Professor.
Yeah, okay.
Thank you.
Yeah. All right. So let's now talk about, many time encryption, or also called chosen plain text, right? Because if you remember, for the attacker can choose multiple different, set of, messages. And what happens is we won't be able to protect our systems against these different messages. So we should be able to encrypt the system multiple times. And even after doing that, the attacker should not be able to tell the difference between the encrypted values. There's a question, so isn't this similar to the seed in Python? If you have used NumPy choice, the seed value determines the random number. Yeah, so there is this pitfall that, random number generator and cryptography secure random number generator are not the same thing, all right? So when we are saying random number generator that you use in your computer, it's not the same idea that we are using in cryptography, right? So for the cryptography, there are other things that we need to consider. So generally what happens is this random number generators that being designed on our computers are not cryptography secure, all right? So that's a different idea. It might be or may not be, right? So just don't assume that this something that is just pseudo-random is cryptography secure pseudo-random. Again, there are mathematical definitions and proof for it. We don't have time for going through it, but essentially the idea is that in terms of distribution, these two have to be very close to each other, and not all the codes that you write in your, just because it looks random doesn't mean that it's actually indeed cryptography secure random, right? Does it make sense, Aaron? So yeah, so we want to now talk about this many time, encryption systems, right? So one idea that comes into mind is one thing we can do is using, different keys for each encryption, and that should solve the problem essentially, right? Because if I encrypt the same message using two different keys, key 1 and key 2, and then that results in two different ciphertexts, and that should be good enough for us, right? And in fact, the answer to that is yes, but the problem is that, unfortunately, it's not feasible. Why it's not feasible? Because for every single message that you want to encrypt, you have to have a separate key for it, right? And then just think about it, like how many messages, how many transactions every day is happening. We need to create a new pair of keys for all of them. And just remember that we are talking about symmetric key systems. So every time that the new key has been generated, we need to find a way to not only use it for our own encryption, but also somehow send it to the decryption, mechanism systems and user, whatever it is, right? So it's kind of like it has to also send there, and that's also a challenge for itself. So having different keys for every single encryption doesn't make any sense. So what we need, as I said before, we basically needs to look at this probabilistic or random looking cipher. So essentially when we are doing that, we are encrypting the same plain text under the same key, the results should be different from one time to another. All right, and we call this semantic security under chosen plain text attacks, which means that if the attacker used two different messages, two different plain text with their own choice, so for example, the same yes, same no, or something else, whatever the attacker chooses, the system should be secure against that as well. So it shouldn't leak any new information, all right? So we call that CPA, or chosen plain text attacks. And if the system is secure against that, we're gonna say that it's CPA secure, all right? And it goes without saying that essentially any sort of system that we are looking for these days, for any realistic system, the system has to be CPA secure. Otherwise, it doesn't make any sense. You can just only encrypt one message, and then you have to throw away your system entirely, right? So yeah, so the idea, I already talked about this, so just one more time. So the stream cipher would look like something like this, that we have some key, we have some nonce, which we call it, which is basically a random number as the input. The input goes into this algorithm G. The G is going to create us this key stream. So it's continuously give us key bits. And then basically what happens here is that we're going to then put our plain text and XOR it with our key, and then get our ciphertext C here. All right. And this process can continue over and over and over again. All right. And then since what happens is that we encrypt one time and we get our C. So the next time that another C comes, you have to make sure that this nonce is not the same value that we used before. So since this part is actually done on the encryption part, right? The encryption algorithm just has to make sure that this nonce is changing each time. All right. And then this way, the data will be different, the key will be different, and then we can just normally do our one-time path and be done with it. So in that case, even if the message is 0 and 0 both times, since this nonce is different, the ciphertext would be different. All right. Any questions here? Okay. And for the decryption, then essentially the same idea happens. So this nonce and this key has somehow transferred to the receiver. And then the receiver is going to also have the same algorithm for the stream cipher. In fact, the stream cipher is like a public knowledge, so everybody knows how to implement a stream cipher. But the only thing that is not public is this key and this nonce. So this two goes into the stream cipher. The key going to be generated. Instead of the plain text, the decryptor has the ciphertext. So it's going to XOR the ciphertext with this key, and then it's going to get the plain text. All right. So this way we're going to decrypt this value. Vishnu?
Professor, is the nonce created each and every time differently?
Yes.
Sorry.
Yeah.
So how is the nonce being transferred to the from the encryption to the decryption place every time? Like, do they do they transfer it over the network or something, or when they generate a nonce for I+1 time, it is the same for both of them? Like,
yeah, so there are multiple different techniques for it. We don't have time to go over it, but the idea usually is there will be some sort of initialization phase between the receiver and transmitter. They both agree on some initial values for the nonce. And after that, they use the exact same algorithm to generate the next nonce. All right. So for example, they both say that what we're going to do is that always, kind of like counter mode, let's say. So we're going to do I plus 1 each time. And the only thing is that this I has to be equal to the number that both of them agrees on at the beginning. So if they're on the same page, just one round of communication, and then after that, they can just continue doing that.
Okay, thank you, Professor.
Yeah, so somebody asked, so now the transmitter must send first nonce, the key, and the ciphertext. No, the transmitter never sends the key with the ciphertext, right? So the key exchange is the process where the transmitter and receiver agrees on some key. And there is another algorithm for that, which we probably going to talk about a little bit later. But there is a separate phase, let's call it an offline phase or key exchange phase, where these two kind of like, share each other's information, key information, all right? So they do that. Now they agrees on the key, and now that's where the actual encryption happens. And this can be only done once, right? So it doesn't have to be repeated every time. Only one time they share their key to each other, and then that's it. And then for the rest of their lives, they can, as long as the key is secure, they can just continue and agree on the same key, right? Yeah, again, exactly. So the key is this key exchange has to be done secure. The nonce doesn't have to be, so the nonce is not a secure value. So you can just, publicly share it with the other user. As I said, both of them has to make sure that they are using the same value at the beginning, and then they're making sure every time that they do the encryption, they change that value, right? So that's the whole point. So usually, again, there will be some sort of handshaking between the receiver and sender, and that's where they kind of agrees on the nonce value.
So can the nonce be publicly available to all the users?
When they're sending it, they usually send it with the same value, yes.
Okay.
Okay. Because the whole point is that this key is the one that actually makes the difference. All right. So now we want to talk about another important primitives, and that's called block ciphers. And the reason that we want to do block ciphers is because it's actually going to give us much more powerful use cases and abilities that we're going to use. All right. So let's see what block cipher is and how it's different from stream ciphers. All right. So in just defining block ciphers, essentially block cipher is this one-to-one functions that maps the domain X to its own. All right. So we have a function that's basically just X to X. All right. So given that, the inputs and output the same, essentially each output would be a permutation of its domain, right? So basically, if you think about this way, we have 1, 2, 3, so on. And then here we will have 1, 2, 3, so on. So basically, this one-to-one mapping would be nothing but, mapping each value to a specific input, right? So doing something like that and continue, right? So that's the idea here for the function. And what happens is basically the block ciphers I'm going to show you. The major difference between the block ciphers and stream ciphers is that block ciphers is much more faster. And the reason that it's faster is just works on, as the name suggests, on blocks rather than streams. So it basically the inputs of block cipher, as we're going to describe, would be something like 128 bits at the same time. And then it's going to encrypt it for us in one go. All right. So instead of like going one by one and then creating the key and then do one-time pad and so on, block ciphers are generally much more faster than stream ciphers. All right. And we can show that essentially if we have a one-on-one function like this, and if this one-on-one function are basically indistinguishable from a random permutation, then we can show that block ciphers can also give us semantically secure encryption system. All right. So what does let me just move one more time, just quickly go over it. So block cipher is just this one-to-one function mapping. It's just a permutation. So it basically maps from one domain to exactly same domain. So it's just, think about it as just some permutation of a list of numbers. All right. And the key part for the block cipher is that if this permutation is indistinguishable for any random permutation, again, there is a mathematical definition for it. We're not going to go through it, but just think about this is that if the attacker queries this mapping, so basically the attacker sends a bunch of different messages, M1, M2, M3, all the way to MQ. So let's say Q is some finite number, and then gets the mapping of all these. Let's call it C1, C2, C3, and C4 all the way to CQ. This mapping should not be distinguishable from any sort of random mapping of these same sequence. All right. So in other words, the attacker should not have a good knowledge of what could come next, right? So you cannot really detect what happens afterwards, right? So this is what the block cipher will give us. So in this case, X is the messages. Yes. So the domain X could be any domain, but you can think about this as that X is basically your message domain, but it also uses your ciphertext domain as well because they're same domain, right? So what we are doing, think about it this way, that I have a number between 0 to the power of 128 minus 1, for example. So 128 bits numbers. What I do is that I just randomly permute this and create this block cipher, right? So if I do this, then I have this encryption mechanism. And if I do it in the correct way, then it will be semantically secure, right? Any questions? Okay. Vishnu, your hand is still raised. So if you don't have questions, just please don't raise it. Kiarash, you have a question?
Professor, I didn't understand the difference between this and the previous one, the stream ciphers. So the stream ciphers was kind of like this. So what is the difference?
It's the side difference. So stream cipher takes key, an input K, and then do G of K in order to create some K prime. And the idea here is that the size of this K is usually some small number such as L, and the size of this is much more bigger number such as L, right? So L is much more bigger than L, right? And then what happens afterwards is just a random, just the same one-time pad that I described before. So at that point, we're gonna do one-time pad of key prime with the message, and then that way we're gonna get the C, the ciphertext. All right, so that's the idea of the stream cipher. The block cipher is basically saying that we have a function f, which is just a permutation of some inputs to some outputs. We don't know what that permutation is, but what it does is that it has to be designed such a way that's indistinguishable from random. We're going to talk about a little bit about how to achieve that. But what happens in that case is that then what happens is whatever m you have, you can just do f of m and get your ciphertext. We're going to show you that essentially what happens is that in order to use this and then being invertible, you need to also have the key ds. So basically the input would be m and s, and then you get c. And then the invert of this, which basically let's call it f minus 1, we're going to get C and S, and then we're going to get M out of it. All right. So that's the idea of block ciphers.
So the stream cipher is one kind of the block cipher because the F is kind of this turning this K to GK and to K prime. You know, it's conceptually is this. Well,
I mean, at the end of the day, all of them are mapping M to C, right? So all of them are mapping some domain to another domain using some secret information, right? So conceptually, encryption is all about that, regardless of what you're doing. The big difference is block ciphers are much more faster because essentially all you need to do is finding this function and evaluating this function very quickly, right? And what you do is that you just take the entire M, which M in this case could be like 128 bits, 256 bits or something, and quickly just find the mapping for it and be done with it, right? So that would be the block cipher, essentially how it would be implemented. Versus the stream cipher is slightly more complicated because you first needs to do this G of S thing. And actually, unfortunately, the implementation of that is not as straightforward as just a simple mapping that we have in F. And because of that, then this process is much more slow. Does it make sense?
Yeah, kind of.
So the difference is this GK here that takes K and just stretch it to K prime is not as fast as this FM here, all right? Just because of the way that we're gonna implement it. And because of that, block ciphers are much more faster than stream ciphers.
I see. Yeah, thank you.
Yeah. So somebody asked, so in stream, the stretch key size is the message length, right? Yes, exactly. So the whole idea is that we need to stretch it such that it's enough for the message to be one-time path, right? So we increase K such that we get to the point K prime should be the same size as the message. Yes, S in this example is the same as K in this example. They're not the same values, but we are talking about some secret value, right? So. All right, any other questions? Cool. So just to recap, block ciphers are this one-to-one mapping that takes some inputs. We're going to use some key, secret key, in order to map this into some outputs, and that would be our encryption. And if this mapping is indistinguishable from a random permutation, we're going to say that this is a secure block cipher, and that gives us semantically secure encryption mechanism. All right. So another generalizable idea of block ciphers is what's called PRF, or pseudo-random functions. The difference is that in block cipher, we said that basically the function f map x to x. So we're basically going to get permutation. Pseudo-random functions just generally say that doesn't have the output domain doesn't have to be necessarily x, but it can actually be any other domain such as y. All right. So if we basically map some domain to another domain, still one-on-one, and it's still indistinguishable from random, then we call this a pseudo-random function, or PRF. All right. So that's the difference between PRF and block ciphers in general. Right. So what the PRF can be used for? So PRF is actually going to be used in a lot of different cryptography primitives. We're going to talk about how we can achieve a PRF, but just think about that's like an immediate use case for PRF would be that G function that we said for stream ciphers, right? So what we're going to do is that, let's say we want to create G of K, right? So we want to expand G of K. So what we can do is that, let's say this F is this pseudo-random function that we have. We can use key as our secret and then just generate some random values, x1, x2, x3, x4, and so on. And then just create, and then just evaluate this function. This will give us C1, C2, C3, C4, and C4 all the way to C whatever, L. And then we just can put them together, and that would be our pseudo-random generator that we want, right? So this would be one stream, this would be another stream, this would be another stream, and so on and so forth, right? So if you want to create a pseudo-random number generator, what we can do is basically, we can just evaluate the pseudo-random function with the same key, but different inputs, all right? Does it make sense? Anybody that has any questions, doubts? Cool. And the reason that we're doing this, as I said, creating pseudo-random generator is not easy, but having pseudo-random functions is much more easier. And that's why we're doing tricks like this. And that's why block ciphers is usually much more faster than stream ciphers, right? So I hope that's obvious. So here's how it will look like in order to use block ciphers to do the encryption, all right? So usually we'll have, for example, a list or vectors of plain text, or we have the large and long plain text. What we can do is that we will divide it into blocks. So let's say that it's like, let's say it's 64 blocks, bits of blocks. And then in this case, we have 3 times 64. That's the size of the message. So we're going to divide it into pieces, into blocks. And what we're going to do is that we're going to start encrypting this. And usually there are multiple different modes for encryption. The one that I'm showing here is called CBC or blockchaining. So what we do is that we encrypt the plain text. We send it to this block cipher encryption with some key, and then we get our ciphertext. In order to create that randomization behavior that I told you, so that next time that we encrypt this, we don't get exactly the same value. At the beginning, we're going to get this initialization vector, or you can call it that nonce that we said before. So what we do first is that we're going to XOR these nonce with the plain text, and that would be the input for the first block cipher. So this block cipher, this function permutation that I talked about, we're basically going to take the key, take the inputs, and create the ciphertext for us. And then we're going to chain this to the rest of the encryption. So basically, this value here will be XOR with the second message, second part of the message. Then it's going to go as the inputs to the block cipher encryption block, same key as this one. Then we're going to get the second part of the ciphertext. Again, this one going to go forward, and so on and so forth. The reason for this chaining is that, as I said, to create this randomness behavior, this probabilistic behavior. And the reason that we are like doing it this way, why we are doing it XOR and so on, again, there are mathematical reasons for it that we're gonna talk about, but just the rationale behind it is that we want to create a probabilistic behavior such that if the next time the same message is being encrypted here, we don't generate the exact same results, right? So basically by changing this each time that we do the encryption, the entire thing, this one, and this one, all of them will be changing, all right? And this is not the only way we can do it. There are other ways such as, a counter mode and so on and so forth that we can do it. So this one that I'm showing here is just what's called CBC mode, all right? Any questions? All right, so what is inside the block cipher? So what is inside these things here? So how these things are being implemented? And the answer to that is something like this. So inside each of these blocks, something like this works. So the input X, this is the X at this point. It's gonna go through what is called rounds. So the rounds is basically the same function that kind of do the mapping, all right? So, and then we just repeat this rounds with different keys, all right? So what happens is that we have a key, which is in this case, this key here. We're gonna get that key and we're gonna expand it using some key expansion techniques. Think about it as the same way that the stream cipher works, but it's not exactly that. It's much more faster and much more efficient than that. So we're gonna get different keys, key 1, key 2, key 3, and key 4, depending on how many rounds we have. For example, for AES, we have 10 rounds. So we have the n equal to 10 in this case. And then we're gonna apply the same function over and over again with different keys. And at some points, we're gonna just output the value y. And this would be the value that we're gonna use. The idea of why we're doing it in rounds, it's actually, there's unfortunately not a clear or mathematical proof for that. It's most like one of those things that kind of like ad hoc in some sense. So like, for example, AES is using it as 10 different rounds. And if you do 9 rounds or 11 rounds, it wouldn't be secure. So they actually show that in order to make this indistinguishable from random, you have to do it 10 times. And there is no answer for it that why 10 times, why nine times, or 8 times, and so on wouldn't work. It's more of empirical to show that this actually works this way. All right. So the answer to how to make a secure block cipher, there is no answer for it mathematically, right? So there's no theoretical response for creating a block cipher that is indistinguishable from random. What it happens is basically people just try different things and show that they can create a function mapping that is indistinguishable from random. But on the other hand, doesn't mean that any sort of ad hoc method that you use will result in something that is indistinguishable from random. It actually takes years and years for people to actually come up with this idea, right? So that's the whole point of block ciphers and how they actually do it in this way. All right. The key thing, there are a bunch of things that people know. For example, these functions should be nonlinear. So people have shown that if this is just pure linear functions, it doesn't matter how many rounds you do, you never get to this randomness behavior that you're looking for. So usually what happens is that there are some nonlinear activity going on at each round, right? So probably if you're interested, take a look at 5-style networks and S boxes. So these are the two key things in order to do this nonlinear behaviors in each of these rounds. All right. Any questions? All right, so let me quickly recap. So in order to get the many times CPA secure, semantic secure encryption mechanism, what we described was, we start with the original one-time pad. It has two issues, key size, right? And many time pad, right? So those two things. Then we said, okay, a solution for this would be stream ciphers, where essentially what we do is that we are saying that, okay, we have a small key. We're gonna expand this to a bigger key. And now we're gonna add this with our message. And then this way we're gonna get our ciphertext. But this again has the issue of if I do it multiple times, I'm gonna get the same answer. So to fix that, I'm gonna add also this thing called nonce here. And this way, if I change this nonce, I can just make sure that this value is changing every time that I repeat this process, right? The problem with this stream cipher is that this expansion of keys in order to be secure is slightly slow. So instead, we are looking for things that is called block cipher. And block cipher is nothing but just a one-to-one mapping of X to some value Y. So basically, it's just what it does is that it's just put this value into another domain. Usually it's a permutation. So it's from domain X to domain X, but it could be from any domain X to any domain Y as well, if you want to do that. And usually we call that pseudo-random functions, all right? So pseudo-random function is going to be using multiple other things, including hash functions and max and so on that we're going to talk about later in the course. But what we want here for the encryption is basically just a function that quickly maps something to another. The way this works is that this actually has multiple rounds. So typically this is done like this, where each round is kind of like a mapping of X to another X. So X1 to X2 to X3 to X4, so on and so forth, until we get to Xn, which is equal to Y, all right? The reason to choose how this network should look like, how many rounds we should use, and so on, this is more of like an empirical analysis that needs to be done in order to make sure that at the end of the day, this permutation is indistinguishable from random. There are known techniques for it, including the very famous AES encryption mechanism, which is basically what it does is that do this process very efficiently. The major thing here is that not only this has to be secure, but it has to be very quick. And as I said, the reason that we prefer and use block cipher is that this process, although it's multiple rounds, they're very, very fast and much faster than this key expansion techniques that we have. All right. So that's why block ciphers are much more popular these days than stream ciphers. And then at the end of the day, if we have chain of messages that we want to encrypt, so let's say that our block cipher works on blocks of 64 bits. And then if we have a message that's, 128 bits, what should we do is that we divide this into 2 blocks, and then we're going to use this chaining behavior. So it's not just, I use block cipher to encrypt this, and I'm going to use block cipher to encrypt this. This won't be secure. There are mathematical and tax proofs for it. So we basically need to do some sort of chaining these two together, which kind of one of these chaining mechanism that has been proven to be secure is this mechanism that I'm showing here, that the input would be XOR with some random value. It's going to go through our block cipher, which is basically this thing here. Then we're going to get the first set of ciphertext. We're going to use this in order to initialize the next round, the next round, and next round, right? So basically this would be a machine that at the beginning takes some random value, but it continues to do that in future, all right? And somebody asked, how does the decryption work? So the decryption is basically nothing but from this side to that side, right? So if we can also find a way to invert this functionality behavior, then we get the decryption as well. So basically all these functions that we have here, they have also an invert function that can be using the key that can be inverted pretty easily, all right? But I mean, the nice thing about the AES is that people have shown that basically both ways going to generate the same thing. So it's kind of like a mirror behavior that it has. We didn't have time to go through the actual algorithms in this, but it's actually a nice thing if you're interested to look exactly how these rounds are being implemented, what is inside each round, and so on. This is actually quite interesting innovation that people have shown. Any other questions? All right, so let's take a quick break, and then now we're going to talk about asymmetric encryption. All right, let's continue. All right, so now let's switch gear and talk about asymmetric encryption and see what are the differences between symmetric encryption and asymmetric encryption. For symmetric encryption, I suggest to mainly look at AES as the most popular symmetric encryption mechanisms and see how, as a block cipher, this is actually being implemented, how many rounds it has, what is through each round, what's the differences, and so on. For stream ciphers, there are multiple different stream ciphers. RC4 was one that's being popular for many years, but then it's people show that it's not secure. So, but if you're just interested to see how stream cipher works, RC4, Cha-Cha, it's another one that's being used a lot, and so you can take a look at those and see how they are actually being implemented. All right. So now let's talk about asymmetric encryption. The main difference between asymmetric and symmetric is that for encryption and decryption, we're going to use separate keys. All right. So for encryption, we're going to use public key, which essentially is not secret at all. It's actually everybody knows the public key of you. And but public key is unique to each person. So it's not like, everybody use the exact same public key. Public key for each person is different than the public key for another person, but everybody can potentially know each other's public keys. Then so this would be after the encryption, that would be the ciphertext. The beauty of the asymmetric encryption is that it's mathematically guaranteed that only the person that has access to the private key should be able to decrypt this message and see the actual content. Everybody else, even if they have access to the public key and the ciphertext, they cannot see what is exactly inside it. So in other words, they cannot encrypt this message, all right? So they only can decrypt, so they only can encrypt a new plain text with the public key, but without the private key, they cannot decrypt, all right? So that's the whole point of asymmetric encryption. So the most important advantage of asymmetric encryption is that then it's completely removed the need for agreeing on the same key. Why? Because essentially, if I want to communicate with you, all I need is that you share with me your public key. I'm going to encrypt my message with your public key, and then send you the ciphertext, and you're going to decrypt this message using your secret key, and then you're going to get the message. So at none of these points I ever need to actually share with you any specific secret. All right. So this public key is known to everybody. So you just send me your public key, or you publish it online on your website or on a storage file or something. If I want to send you a message, I'm going to go and grab it. I'm going to encrypt the message that I have with that and send you the ciphertext. And you will be the only one who, using your secret key, is going to be implemented to decrypt. All right. The similarity between them is that still the same correctness requirements is needed. So basically, the encryption of a message should be equal to M, right? And then keep in mind that here we are encrypting with public key, but we are decrypting with secret key. So it's slightly different. But at the end of the day, the message that I encrypted should be the exact same message that you're receiving. For semantic security, actually, this is not exactly equal to M. So actually, it's kind of like M with some error epsilon. So in rare cases, it might be not exactly correct. Yeah, so in other words, in some case, in epsilon, with epsilon probability, you might actually get a different message, which is the error, obviously. But if, again, this epsilon is very, very small, in order of 128 or 256 and so on, this won't happen ever, basically, almost never, right? So that's the idea here. And we're going to get the same security guarantee. So basically, we are looking for semantic security for asymmetric system as well, although we need a little bit more, as I'm going to describe in the next few slides, that why we need slightly more, stronger guarantees in asymmetric encryption. All right. Any questions so far? Cool. So the big difference between symmetric and asymmetric encryption is this thing called chosen ciphertext attacks. All right. So that's the big difference between these two, is that in symmetric encryption, the idea was chosen plaintext attacks, where we just say that the attacker can use different messages such as M0, M1, so on and so forth, then query the model in order to get the encryption, and then just see whether it can detect whether C1 is M1 or C1 is M2, and so on and so forth. So that's where we said that, there was a chosen plaintext attacks that we need to make sure that we are capable of protecting the systems against, right? So we said that all we need to do is that for the attacker not being able to distinguish between C1 and C2, if it sends us M0 and M1, right? So that was the chosen plaintext guarantee that we want. For the ciphertext attacks and for asymmetric systems, the difference is that since the attacker also has access to the public key, the attacker not only can send multiple different messages, but the attacker can also encrypt this and get access to the ciphertext as well, right? Why? Because essentially, in order to encrypt something, I just said that all you need to do is using the encryption message and the public key. And all of these things are known to the attacker. The encryption mechanism is a public knowledge, public key is public knowledge, and message is what the attacker can choose. So in other words, what happens is that the attacker not only has access to M0s, but also has access to pairs of M0s and C0s and C1s and so on. So MI and CI, right? So it has access to all of this, but of course it has access to finite number of these, right? And we want to get security under this assumption, which basically is saying that even if the attacker has access to all of this, Still, if the attacker has, you know, a new message and let's call it MX and CX, without, and then so let's say MX1 and this MX prime and CX prime, something like that. And then if the attacker gives, so basically with this, all these lists, the attacker should not be able to again decrypt a new ciphertext. Let's call it CY or something like that. So what we want to do is that although all the list is already there, the attacker should not be given a new ciphertext being able to say which message this one belongs to. All right. And then again, here we are assuming that, you know, the domain for the message in ciphertext is so big that it's not just searching with like normal searching would work, right? So it's because let's say we are talking about 256, 512 or something like that, 2 to the power of those. So these are the number of possibilities that the attacker needs to search through. And this is so big that it takes years and years to find the solution that the attacker wants, right? So it's kind of like what I just described. So in symmetric key, the attacker cannot choose the ciphertext, because if the attacker has access to the key, then the problem is kind of solved. So it can only choose set of messages, but cannot choose what is the corresponding ciphertext to it. But in the public key cryptography, not only the attacker has access to the messages, can actively choose the ciphertext as well and query the systems multiple times. But even under this assumptions, we want the system to be secure, all right? So this is like a more formal CCA, secure chosen ciphertext attacks secure. So we are saying that if the attacker has finite pairs of MI and CI, he still should not be able to decrypt a random message. And of course, that random message should not be part of this this pair, right? So if we're given a random message, he or she should not be able to decrypt this message, right? So that's what we are saying, CCA secure, and this is an additional guarantee that we need to have in our asymmetric system. Any question here so far?
I have a question.
Sure.
So for the same messages, the cipher. So, for example, we have the exact same message, and we encrypt it with the same key. So the cipher will be equal to each other. So there is no nonce or this kind of thing that makes sure the cipher will be different each time.
No, it will be. So again, the asymmetric will be, the encryption mechanism in asymmetric will be also probabilistics. So which means that if I encrypt the message twice, I will get 2 different ciphertexts. I'll talk about that part.
Okay.
But here what I'm saying is that let's say we have different set of messages. We just keep encrypting all of them. We get set of ciphertext, right? So we have list of M and C's, pair of MCs. What we are saying is that if you have this finite list, then if there is new random message that being encrypted, the attacker should not be able to decrypt that. All right, so that's what we want to achieve with CCA secure. So somebody says, what is preventing the attacker from testing all messages and getting all ciphertext using the public key? Nothing. What is, as I said, it's 2 to the power of 256, which takes 100 million years to do all the tests. All right, so that's the whole point. So that's the whole epsilon part. So it's not 0. It's really, really small, and it's not feasible for the attacker to do that. So basically what happens is that exhaustive search is the best tool that the attacker can use in all these encryption mechanisms. And if we make that exhaustive search so big, then we kind of like get the security that we want. So if you, for example, check here, this mechanism, you'll see that, for example, you see numbers like it will take 30 years for encryption mechanism to be broken or something. That's the idea here, that, the attacker will search through all the different possibilities. And in order to do that, let's say, for example, it takes 1 millisecond for every search. Then there's this and such number of search that needs to be done, and if they multiply these numbers, you get to that number 30 years. Hey, Harry. Oh, your voice is so faint. So probably your mic doesn't work or something.
Hello, Professor, am I audible?
Now we can hear you.
Yep. So this is from the previous slide. Like where we told that because of the epsilon factor, the decrypted message might be like having a small error, which is like tolerable. I mean, will the errors be correlated each time we encrypt a message? Will the errors be the same, or it's again probabilistic thing?
Yeah, it's a problem. So it's not like if you do multiple times, at some point you'll get the error. It's always epsilon probability that you get the error. They're independent.
Okay, got it. Because if it were dependent, we can maybe like encrypt the message 2 times, and like if we subtract, we can cancel the error or do some sort of thing.
No, you never get error for every single encryption. What I'm saying is that you either get the correct message or you get garbage.
Oh.
Okay, so you either get M or you get garbage. All right.
Okay.
And the probability of getting correct message is 1 minus epsilon, and the probability of creating garbage is epsilon. All right, each time that you do the decryption. And what we are saying is that this epsilon is really, really small number. So you essentially in real world, you get almost 1. All right.
Almost 1.
And it's not something that you need to worry about. I just made this comment to make sure that we are accurate. But in real world settings, almost there's no. It's not something to be worried about.
Okay, thanks.
Yep. So we want the message domain to be really large. Yes, that's what we do usually, right? So that's why we need to choose things like, so the size of the bits that we use matters, right? So when we are talking about 256, 512, and things like that, we are talking about this. So we want this to be large enough so that the exhaustive search will take really, really long time. But on the other hand, you don't want to make them arbitrarily large, because essentially then your encryption and decryption takes more time, right? Because think about this, is that kind of like the latency for decryption or encryption is also a function of the size, right? So you don't want to make this arbitrarily large size, because then your latency will be affected, right? So that's like you need to find the minimum that gives you the security that you want, right? Can quantum computers break this encryption? We're gonna talk about that. Yes. So later on we're gonna talk about quantum computers and what happens with quantum computers. But yes, you're right. What happens is this is for normal computers, and then when we're talking about quantum computers, that's exactly what happens. So, I actually in the next few slides, I'm gonna a little bit talk about that. All right, so it would be a good practice for you guys to think about the CCA security adversarial game. So we're gonna have an adversary and a challenger. Just think about it, whether you can actually create this game between these two. And I'm not gonna give you the answer. Just try it for yourself, and then you can just either Google it or post it on campus for the correct answer for this. All right. So take some time and think about this adversarial game. So just the thing that I just said here, see whether we can reduce it to the adversarial game that I described before for you. All right. See whether you can find this or not. Okay, so now we kind of need what to look for. Then the question is, okay, how to build a public crypto system, right? What we're looking for is basically we need some sort of functional algorithm that should be very easy to compute, but should be very hard to invert. Why? because essentially this would be the idea of public key and private key. So what we want is some function f that if we give that function m and some public key, it will give us c. So evaluating that function would be very easy, but it would be very hard to do c and get the value. All right, so this should be very hard, but this should be very fast and easy. All right, and that if that's the case, then we have our encryption system. And then how do we do the decryption? Then it basically is to be hard without some secret, let's call it secret key. It should be hard to get this without that, but it should be, again, easy with that. So it should be easy to do this. Okay, so we want these two functionality, but we don't want this functionality in the middle, right? So we should be able to have a function f that's, if we give m and pk, it quickly gives us c, but it should be very hard to find the inverse of that function and find m given c and pk maybe. And also it should be easy for us that for some other secret sk, we can quickly invert that function and get m, right? So that's what we're looking for in the asymmetric encryption system. And the very interesting thing is that there exists such a function, although it doesn't seem very intuitive. And we usually call those a trapdoor or one-way functions, all right? So one-way function or trapdoor function is exactly what I described. To give you a little bit more formal definition, we usually call a trapdoor function, or T, a function that is defined over x and y. So basically it's T, x to y. And it has three pole of algorithms, G, F, and I. So let me go through what each of these does. So G is a probabilistic key generation algorithm that is just randomly create a pair of S and PK. All right, so it's just this function that creates a pair of SK and PK for us. All right. And there is some, it's not just, PK and SK are independent from each other. It's actually, they are dependent from each other. And G is actually create this for us, but it's just randomly create this each time we query G, right? So that's the first step. The second step is the function F, which is actually a deterministic algorithm that when it's invoked, if we send PK and X to it, it will give us Y. All right, so F is just doing that. And I is again a deterministic algorithm that if we send SK and Y to I, it will give us X. All right, so this is the whole point of a trapdoor function. It's a function that is defined from X to Y, from domain X to domain Y. Triple algorithms that exist in a trapdoor function. G is what's called a key generation algorithm. That what it does is basically from random distribution give us SK and PK, which is kind of related to each other with some specific algorithm that G decides. Then now we have the SK and PK, which we call PK public key and SK secret key. Then what we're going to do is that we're going to have another function called F, which is a deterministic algorithm, which essentially if you give PK and X to it, it will give you the Y. And then there is I, which is kind of the inverse of F in some sense, which if you give the I, SK, and Y, it will give you the X, all right? So the important part is that this F and I is kind of one-to-one functions. So basically, again, we are mapping, the trapdoor function is basically a one-to-one function. So we are mapping elements in X to elements in Y in some models. So basically F and PK does that for us. Doesn't necessarily has to be exactly same permutation. So it doesn't have to be X to X. Y can be much more larger than X. So all of that matters is that if for all the elements in X, there will be a counterpart in Y, but there could be scenarios that there are some elements in Y that is not mapped to X, and that's totally fine. All right, so that's what we care about. as I said, it could be a permutation if X and Y are exactly the same size, but it could be just generic type of definition as well that necessarily doesn't have to be a permutation, all right? So the little letter on G is R. So when we are doing something like this, we are saying that we are sampling at random from this function, from this distribution, right? So this is the notation that we typically use. So there is some distribution. We are sampling at random from this distribution to get those values. All right. So that's why it's a probabilistic algorithm. All right. So the idea is basically, as I said before, the security of this comes from this fact that F should be one way, in the sense that with PK, we should be able to evaluate this trapdoor function, but without SK, we should not be able to invert this trapdoor function, all right? But with SK, we should be easily to invert this. So I give us this opportunity, but without SK, it should be difficult or hard for inverting this function, and that's all we want. Any questions here for trapdoor functions?
I have a question, Professor.
Yeah.
So the dimension of the keys must be very large, because with the exhaustive search on the keys, the adversary can get the keys because they are correlated with each other, the secret and the public, and they have access to the public keys, right?
Right.
Okay, thank you.
Any other questions? All right, so yeah, just keep in mind that it's always exhaustive search is a tool that the adversary has. So it's always you can do that. So how to prove the security of the trapdoor functions, how to say that, okay, if I say this, how do I prove that this T that I'm saying and claiming is a trapdoor function? And the trick is usually showing that the inverse function, whatever trapdoor function that we are proposing, the inverse of that function is reducing to some known problems. The very famous examples that probably all of you already heard is the RSA, for example, trapdoor function, which essentially reduced to the factorization problem, right? So the factorization says that if you have a large n, it will take a lot of time to actually factor it to its prime factors P and Q. If this n is large enough, finding these prime factors will take a long time, all right? In a matter of years and so on. Right. So basically, the way that this RSA is designed is basically saying that if somebody can invert the RSA function, they can solve this factorization problem, and this will reduce to some NP problem. So it kind of goes back to that NP hard and NP completeness that you probably all of you have heard. So basically, given that there's no known solution for that, there's no known solution for this, and then there's no known solution for the inverse of RSA function, so that the inverse function, so RSA function is a secure trapdoor function, right? Same story goes for Diffie-Hellman, which is also another very popular mechanism, which kind of reduced to discrete logarithmic problem. Again, that's reduced to some other NP problems and same story and so on. All right, there are some others as well. All of them kind of relies on this fact that if you're able to inverse these functions, then you can solve some NP problems that is shown to not be able to solve. At least we don't know any solutions for it. It could be at some point in future somebody comes up with solutions, but at least for now, we know that there is no known solution for it, right? So that's where the security of these things is proven. Once we prove that the trapdoor is secure. Once we prove that the trapdoor is secure, there are mechanisms for showing that we can achieve semantic security and all those good stuff that we discussed, all right? So that's where the security of these things really rely. Any questions? All right, so let me just quickly go over some real world encryption mechanisms. So one easy thing to do is, in order to use public key encryption, you can use what is called a hybrid method. So the trick is this. So the trick is that if I want to encrypt a message, I don't use it directly using public key encryption. What I do is I'm gonna encrypt a key, a random key. So this is just a random number. I'm gonna encrypt this using the public key, and I'm gonna call that C, right? And then I'm gonna use this to encrypt the message as well. All right, so whatever that message is, I'm gonna use this to encrypt this message, but the trick is this is asymmetric encryption. So it's not asymmetric, it's actually symmetric. So this is, for example, AES. And I'm gonna send C prime as well. So I'm gonna send a pair of C and C prime to the receiver, all right? So what the receiver does, the receiver gonna take this C, gonna decrypt it using the secret key, and he or she gonna get K out of this. Remember, we encrypt K using public key encryption and get C. So if we decrypt C using secret key, we're gonna get K. And now we're gonna get this K and this C, and then gonna decrypt this using symmetric encryption mechanism, again, AES, all right? And now we're gonna get our message, all right? So that's the hybrid methods that's quite popular. So instead of actually, encrypting everything using public key cryptography, we are only encrypting the key using public key cryptography, and then decrypt the key using public key cryptography, and then use that for symmetric, all right? And the reason for that is that generally public key encryption is very, very slow, order of magnitude slower than symmetric key encryption. So in that case, if you want to, decrypt and encrypt a really large message, usually it doesn't make sense to use public key encryption. So what I would do is that kind of using this hybrid methods, and everybody would be happy. And the interesting thing here is that this is still a public key mechanism. It's an asymmetric and public key. The reason for it is that we never agree on this key, just this key has been generated randomly by us as the encryptor, right? So even though that we are using symmetric, we don't need to send the symmetric key beforehand. On the fly, we create this key, we encrypt it using public key, then we send that, and we send this C. So the trick is using both of them, sending both of them to the receiver. Does that make sense? Anybody has any questions? All right, so that's the hybrid method. So another important consideration for asymmetric encryption is that for security reasons, the message should be uniformly distributed. And the encryption obviously has to be randomized. And in the encryption and decryption of long messages has to be efficient. So these are the main three consideration that we need to make. And as a result, this would be how the asymmetric encryption would work. The way that it works, so this is not the hybrid method, this is just a normal public key encryption. So what we do here is that we don't, again, directly apply public key encryption to the message. What we do is that we first create this random value called X, all right? So that's the first step. Then we're gonna use some sort of a function, which is like, for now, let's call it a hash function, that this hash function given X gonna give us this key. So think about this as some sort of like, key expansion techniques. Then we're gonna have our key. And what we're gonna do is we're gonna use this key to encrypt the message and get C. And then what we're gonna do is also we're gonna encrypt X with public key and create Y, and we're gonna send Y and C to the decryption receiver. All right. And for the decryption, the first steps is given Y and secret key, we're gonna get X first. Then, since we have the access to the same H, we're gonna put X to the HX, and then we're gonna get key. And then we're gonna decrypt it in symmetric way using C and K, and that's why we're gonna get the message. All right. So that's typically the way that asymmetric systems works. And the reason for that, the reason for that is these three considerations. So we cannot directly apply, trapdoor functions to messages, because typically the messages are not uniformly distributed. Think about this as words that you use in English. It's not definitely uniformly distributed among all the characters, right? So this trick that we use, this X that is being uniformly distributed from some distribution X, that's where we fix this issue in some sense, all right? And this way we're going to create this that is secure, all right? So there are mathematical proofs that shows that if you didn't follow these steps and just do the f of m instead of f of x, the system won't be secure, and in fact it will be broken, all right? So that's why we use x as some sort of like intermediate value. We use x, from x we created k, and then from k we actually do the encryption, all right? So that's the whole idea of asymmetric encryption. If you're interested to know more, you can take a look at the RSA or elliptic curve cryptography, ECC. These are the two main popular methods for asymmetric encryption. Both of them are based on the trapdoor functions. This one's based on the RSA trapdoor function. This one is based on Diffie-Hellman trapdoor function. So if you're interested how it works, you can check it. Yeah, both sides needs to know H. H is public algorithm again, so it's not something that is secret. All right. So H it's a hash function in some sense. This is public to everybody. Same as D and F. All the algorithms that we use here, all of them are public. Everybody knows everything about it. The only thing that they don't know is X and SK. All right. Okay, so that's the end of the encryption and decryption. There are other things that are also important. So very quickly, I'm going to go through it, and then maybe sometime later we're going to talk about it. Another very important primitive in encryption is what's called MAC. So this is called message integrity or message integrity codes. So the idea is that, let's say Alice and Bob wants to talk to each other, send a message. They don't want necessarily to encrypt the messages, but the only thing that they care about is that making sure that this message has not been modified along the way, right? So how do we do it? So additional to the message, we're going to also send a tag. And then we're going to do some algorithm, this G, that essentially given M, it's going to create us a tag. So that's how we create the tag. We're going to send the tag with the message. And then on the other side, there's the verification function, which given M, it's going to, again, calculate the tag. And then I'm going to check whether this tag is what is the expected tag or not. All right. So that's what we are interested to do. Essentially, the idea is that if the attacker changes M, the tag will be different and cannot change the tag. Or if it changes both of them at the same time, it cannot find the correct message tag pair. All right. So the whole security of this is coming from this fact that the attacker cannot generate valid message and tag pairs unless it knows some secrets that only Alice and Bob knows. All right. So that's the idea of the message integrity. We don't have time to go through the details of it, but just know that message integrity is also another important parts of cryptography, where you don't necessarily need to encrypt, but what you care about is that making sure that the value has not been modified. All right. Another important thing in cryptography is hash functions. So hash functions is basically this function that you send an arbitrary size value and it gives you what is called hashes, which is this a fixed size values. So hashes necessarily not used in cryptography, can be used in anything else. The idea is that you want to save space. You want to make sure that all the sizes are the same and all those things. So hashes actually have lots of different use cases as well. But for secure hash, what is important is this thing called collision resistance. So basically the idea of the collision resistance is that we should not be able to find two pairs of messages that have the same hashes. All right. So we say that something has a collision if for M0 and M1, the hash of these two are equal to each other. So that's a collision. And when we are saying something is collision resistance, the idea is that, you know, the probability that we can find, so given a hash function, the probability that the algorithm A can find two pair M0 and M1, that their hashes are equal to each other is negligible, all right? So that's the idea of collision resistant hash functions, right? So we want to have secure hashes for multiple different applications, which we're going to talk about later on in next lecture, on Wednesday. But the idea here is that, you know, we want this H function that would be very, very hard for an attacker to find two pairs of inputs that manage to get the same output, right? So that's the idea of secure hash function. We don't have quite much time. We're already over. So if there is any questions, please ask. That's otherwise, you're free to go, and see you guys on Wednesday.